So now we'll continue with our lesson with molar enthalpy change. What we need to start with though, since you heard the word moles, we're going to be kind of going back to grade 11 and stoichiometry. So first things first, let's remind ourselves what a coefficient is. A coefficient is the number preceding a chemical formula of either a molecule or an atom, and it designates how many moles of that substance is required in the chemical reaction. So for our purposes here, we've got 1 mole of hydrogen gas and half a mole of oxygen gas combining together to make 1 mole of water vapor. The other important thing that you may not have seen before is the fact that we have an energy term in our chemical equation. And this energy term makes this not just a chemical equation, but now it's a thermochemical equation because we've added the energy term. So the minute that there's kinetic energy involved, it becomes a thermochemical equation. The other thing you need to realize is that the fact that this energy term is a product means energy was made with the chemical reaction and it was released. So we can call this an exothermic reaction. Okay, because my energy term is in the product. If it was in the reactant side, it would be an endothermic reaction because you need the energy to have reactants be converted to products. All right. So piggybacking off of what we talked about in the earlier lecture, sorry about that. We've got molar enthalpy, and molar enthalpy is the enthalpy for 1 mole of a substance. So the energy change that happens when 1 mole of a substance undergoes some kind of physical or chemical change, okay, or nuclear change. And when we talk about molar enthalpy, so this guy is going to look different from just plain old delta H. The minute you see a subscript X, and now that X is not always going to be X. It's going to describe what kind of chemical reaction is happening, or what kind of reaction, not necessarily chemical, is happening. Okay, so the minute you see a subscript, you know we're talking about molar enthalpy. So let's take a look at this chart. All right. And this chart comes right from your textbook. And so what you're going to see here is the molar enthalpy for the first one of solution. So you see delta H and a little subscript SOL. So if we look on this side right here, we're seeing that sodium bromide crystal is being dissolved in water. So it's going into solution. So that's why we can use this as the delta H of solution. Same thing for the next one. So that was 1. Let's look at 2. For combustion, we are combusting 1 mole of methane, okay? And here's the other thing. Molar enthalpy refers to 1 mole. So in each case of you seeing this red, it's for 1 mole of sodium bromide here, 1 mole of methane here. And when we're talking about vaporization, so see the delta H of vaporization, 1 mole of liquid methanol evaporating to gas. Formation, this one is an important one. We're going to talk about this one a little bit later on in the chapter. But what you're going to see when you're forming something, it's on the product side. So that's the only one we're kind of dealing with on the product side. You're making it. And just so you can refer to it later, we're always making it. So forming from elements. Okay, so what you're going to see here is we're actually taking the actual elements that make up, in this case, our liquid methanol. All right, so carbon, hydrogen, and oxygen. And the other thing you're going to notice is that these are the state of the elements at room temperature. Okay. Next one, I'm going to couple these two together. These are the molar enthalpies of neutralization from 2 perspectives, either from the acid perspective or from the base perspective. And this is the same reaction, only in each case we have to talk about 1 mole. So that's why when we're talking about the base, we have to divide it by 2 because we need 1 mole of base. And so that results in a half a mole of the acid. Okay? So that's what we're talking about when we say molar enthalpies of reaction. You're going to see the difference because it'll be delta H with a little subscript of whatever type of reaction it's going to be. Okay? So same deal. My delta H's, if they're exothermic, it's going to be negative. And if we're talking about something that's endothermic, it's going to be positive. All right. So moving on to the next page here. Alrighty. Now, the actual magnitude, the number, the amount of energy involved in a change depends on how much matter you're talking about. Because don't forget, everything is based on the number of moles. So obviously, if you are blowing up 1 gram of substance versus blowing up a kilogram of substance, if you're blowing up that kilogram, you're going to make a lot more energy than just 1 gram. So that's what we're talking about with the amount of energy involved. The more substance you have, the more capability there is. Okay, so let's take a look here. When we're talking about water here, and we've got 1 mole of water in the first equation, 2 moles of water in the second equation. Since we've doubled our amount of water, we are going to double our amount of energy released. And how do I know it's released? It's released because we've got a negative delta H. Okay, and if it's a negative delta H, then we know it's exothermic, and we know exothermic means that energy was released. Okay, and just so you remember, N means the number of moles. All right, so you're not allowed to forget what you learned in grade 11. Not allowed. Oh, but look, just in case you have, let's do some review. All right, so review. The mole and amount concentrations. I'm sure, familiar with Avogadro's number. So Avogadro's number is 6.02 times 10 to the power 23 entities per mole. Now, those entities can be whatever you're looking at, right? So if it's an ion, it's an ion. If it's an ionic compound, that's a formula unit. Okay, if it's an atom, it's a neutral atom. And if it's a molecule, this would be my covalent compound. Okay, molar mass is the mass of 1 mole of the substance, and our unit in this situation is grams per mole. Okay, so where do you find this information? Well, you'll look at your periodic table. So this is your atomic mass. Okay, so for instance, just to remind you, the molar mass of H2SO4, what we're going to do is we're going to go to our periodic table, and we know we've got 2 hydrogens, we've got 1 sulfur, and we've got 4 oxygen. Okay, so when I go to my periodic table, I'll have 1.01 grams per mole for the hydrogen. I will have 32.07 grams per mole for my sulfur, and 16 grams per mole for my oxygen. And in each case, I'm multiplying that molar mass by the number of those particular atoms. So when I do my mathematique, I get 98.09 grams per mole for sulfuric acid. All right. So what this means is for every mole of sulfuric acid, that quantity weighs 98.09 grams. So more recap of grade 11. Let's remind ourselves of 2 triangles. Okay, number of moles equals mass over molar mass. And we all remember magic triangle. You can put your finger over whatever variable you're looking for. Okay, so for our situation here, we've got N equals mass over molar mass. Mass equals moles times molar mass. And molar mass equals mass over N. Okay, so we've got that. We also need to remind ourselves about the second triangle from grade 11, which is concentration of a solution. And our magic triangle for that bad boy is, okay, and don't forget, that both of these triangles are linked by my number of moles. Okay, so we can always link these two triangles together. All right, so we have concentration equals moles over volume. We also have moles equals concentration times volume, and volume equals moles over concentration. Okay, so I'm just going to go back to purple. All right. Lastly, calorimetry and molar enthalpies. This is going to be something new. So that was the grade 11 review. Now we're moving back into grade 12 thermochemistry. So if you can recall, the enthalpy change of the system, so I'm going to put system here, is equal to, so the magnitude of the enthalpy change is equal to the heat found or transferred to the surroundings. But I'm going to actually get rid of this, because what I want you to also know is that these guys are opposite. So what that means is my enthalpy change in my system, whether it loses energy, that means the surroundings gained energy, or if my system gains energy, that means my surroundings lose energy. It's a yin and a yang, all right? And so for that reason, I'm going to put this negative here, because I want you to always be aware of the fact that yes, they've got the same magnitude, so the same amount, but their charge is different, or their sign, not charge, their sign is different, because one gains, the other has to lose, the other, or one loses, the other has to gain. Okay, so the other thing, the other equations that we're going to be working with here is the delta H. So this is my enthalpy change. Oops, let me just spell that right. Hold the phone. All right, go back to here. Enthalpy change equals the number of moles times the molar enthalpy. All right, so which makes sense, because the number of moles times the molar enthalpy should be the same. You should get the same units. Also, delta H equals negative Q, and Q equals MC delta T. So when we are doing a calorimetry question, we can group all of these equations together, okay? And for our purposes, we will use N delta HX. So what is this? This is the moles. Whoops. Sorry about that. This is the moles times the molar enthalpy. So you'll end up with delta H. And this is Q. So this is just us saying the delta H of the system equals negative delta Q of the surroundings. Okay, so that's another way to say it. Okay, and remember, this is my system, my chemical system, and this is of the surroundings. So, like I was alluding to before, there's a couple of assumptions we have to make the math nice. Number one, we assume that the surroundings are in a calorimeter in water. Remember, I drew that. I have the water. I have my little system here. We assume that this water, this surroundings, acts like water. So that makes our math easy, because then we know what the density is, and we know what the specific heat capacity is, right? Density, specific heat capacity, unless you're told differently. Also, you assume that we're dealing with an isolated system, right? So heat and matter can't go in or out. It is what it is. Lastly, that whatever made up your calorimeter is also not involved with heat exchange. Those are three major assumptions we make. Okay, so those are big ones. So math time. Let's do it. So number one, calculate the enthalpy change. So we're looking for enthalpy change involved in vaporizing 17.2 grams of liquid mercury. The molar enthalpy of vaporization of mercury is this. So first off, what do we know? Well, we know that my mass of mercury is 17.2 grams. We know the molar enthalpy of vaporization is 59.3. Now take a look at my units, kilojoules per mole. All right. What else do we know? We know the molar mass of mercury. And I looked this up. I'm saving you the trip to your periodic table. Is 200.59 grams per mole. Okay. What are we looking for? We are looking for the enthalpy change. So we will use this formula right here. Delta H equals, all right, so let's think about this. Enthalpy change equals moles times the molar enthalpy of vaporization. So when I plug this in, we need to figure out the number of moles first. So this is a part that we need to remember. So don't forget, moles equals mass over molar mass. 17.2 grams divided by 200.59 grams per mole. And bam, bam, and once again, so my number of moles of mercury is equivalent to, all right, so I've got my number of moles. So now it's just a matter of plugging it in. So when we solve, all right, so that's my number of moles of mercury, and I get my molar enthalpy of vaporization from the question, or you'd be given a table and you'd have to find it, but it was given to us in the question. So 59.3 kilojoules per mole. When I cancel units out, you'll see that my units of enthalpy change are in kilojoules, and okay, you'll see that it's not per mole, it was 4. So what this is saying to me is that the enthalpy change for 17.2 grams of mercury is 5.08 kilojoules. Okay, so that's how much energy is required to convert liquid mercury to gaseous mercury for 17.2 grams. Okay, that's what that means. All right, I'm breathing, you're breathing, we're good. Moving on. So, next example. Just to remind you, I went to 3 significant digits because that was the number of significant digits in my measured quantities in the question. So, I'll just put a little 3 significant digits there so we remember that. Moving on. Exemple 2. What mass of sodium chloride would melt while absorbing 30,000 joules of heat? Okay, so what do we know? Well, we know that the molar mass of sodium chloride is 58.44 grams per mole. We get that from our periodic table. Okay, we also know that my enthalpy change is 30,000 joules of heat. Now here's the other thing. We know that it was absorbed. So if we know it was absorbed, we know that this is a positive number. Okay? And just to make life easy, we can also put this in to kilojoules just to make there are fewer zeros to deal with. Okay? So what else are we looking for? We are looking for the mass. But in order for us to do that, we need another piece of information. Okay? Because ultimately, we need the molar enthalpy of melting. Okay, so I need to go to a table for this. And for me to look up the table, I will show you that I'm just going to cheat here because I've already got it on the side. It is 27.2 kilojoules per mole is the molar enthalpy of melting of sodium chloride. So I got this from a table, and you'd be given this in a question or on a test. All right. And the reason I need this value is because we are going to end up using a specific equation. So we're looking for mass. The equation we're going to be using, though, is once again the same one as before. Delta H equals the moles times the molar enthalpy, and in this case, molar enthalpy of melting. All right, so we know delta H, we know the molar enthalpy of melting. We're going to solve for N. Okay, so let's do that. So N equals okay, so when I do that, I've got 30 kilojoules and 27.2 kilojoules per mole. So there is a reasoning for me in making that 30,000 joules into kilojoules, because that's the value of my molar enthalpy, right? So you want to make sure you're always dealing with the same units so they eventually cancel out. So when I cancel these guys out, N will equal 1.10 moles. So now that we've got this part, it simply is a grade 11 question. So step 2 is figuring out my mass. No problem. Mass equals, and if we go back to our earlier triangles, mass equals moles times molar mass. So when we do that, 1.10 moles of sodium chloride. And the molar mass lovingly provided to you by your teacher is right here. Grams per mole, bam. Okay, and then when we do that math, I get 64.284 grams. And once again, in this situation, here's my measured quantity, 3 significant digits. I will go to 3 significant digits, and so my answer is 64.3 grams of sodium chloride will melt while absorbing that much heat. Okay? All right, next question. There's 2 more. So now, in a calorimetry experiment, now this is a biggie. Calorimetry experiments, there's always questions like this on an exam. And in first year, you're going to have to do calorimetry questions as well. So let's just make sure we understand what's going on first. Okay, so let's read the question first. So we've got 7.47 grams of potassium chloride, and I'm going to draw it here. So here's our calorimeter. We'll have a lid because we know it's an isolated system, and it's dissolved in 100 mils of water. Okay, so here's my water. There's my 100 mils of water. Here is my 7.47 grams of potassium chloride. Okay, so that's where that is. We stick in our thermometer. Okay, and so originally the water was 24.1 degrees Celsius. The final temperature of the water, sorry about that, the final temperature of the water is 20 degrees Celsius. Okay, so the water got cooler. So if the water got cooler, was this an endo or an exothermic reaction? Well, if my water got cooler, that means the water or the surroundings gave energy to the system. So that means the system absorbed energy. That means this is an endothermic reaction. Okay, so for our purposes, this is my system, and the water is my surroundings. Okay, all right, so let's do the math. What do we know? Well, we're given that the mass of potassium chloride is 7.47 grams. Just to get this out of the way, we know our molar mass of potassium chloride is 74.55 grams per mole. We also know that the volume of water is 100 mils. And this translates to 100 grams because we know the density of water is 1 gram per mil. We know the specific heat capacity of water is 4.18 joules per gram degrees Celsius. And what else do we know? We know that T1 is 24.1 degrees Celsius, T2 is 20 degrees Celsius, so therefore we also know that delta T in this situation is T2 minus T1, which is negative 4.1 degrees Celsius. Okay, so what are we looking for? Well, we are looking for the molar enthalpy of solution. Okay, so what we're going to do, the way we analyze this, is we know that delta H equals negative Q. Another way that we can manipulate this is that delta H equals the number of moles times the molar enthalpy of whatever reaction. So I'm going to put an X there. And we also know that Q equals MC delta T. So when I manipulate all these equations, I can say that for this particular equation, my moles times my molar enthalpy of solution will equal negative MC delta T. Okay, and remember, their signs are opposite because one gains, one loses. All right, so back to this. Let's solve. So I got to figure out my number of moles first. So my number of moles, actually, do I need to do that? I guess I don't have to. We can solve here. So, sorry about that, guys. All right, so I will do my delta H of solution equals the negative mass. And this is the one thing you need to remember. When we're talking about Q, this is about the water. And when we're talking about this side, this is the system. So when I talk about the MC delta T divided by N, because that's what I manipulated, this is for the water. So my mass of the water is 100 grams. Okay, times 4.18 joules per gram degrees Celsius times negative 4.1 degrees Celsius. So far, do you see where everything came from? We're playing with 100 grams of water. There's the specific heat capacity for water and the temperature change of the water. And now we're going to determine the number of moles because that's the one thing I didn't do. So number of moles of potassium chloride is mass over molar mass. So 7.47 grams divided by 74.55 grams per mole. And so my number of moles is equal to 0.10 moles. Oops, I'm just going to get rid of that because that's kind of messy there. Oops, I got rid of everything there. All right, so now we know we've got 0.10 moles of potassium chloride. Okay, so when we do all this math, and just because I like doing it, let's cancel out like terms. Bam, 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 bam. So when we actually do the math, we end up getting 17.5 0.138 joules per mole. Okay, you'll notice my negative sign multiplied by my another negative sign cancel out, and this is positive, which makes sense because we talked about it being an endothermic reaction. So let's go to significant digits. I've got 3 significant digits, so 1.71 times 10 to the power 1, 2, 3, 4. Okay, so you can keep it in joules per mole, or you could say 17.1 kilojoules per mole, whatever floats your boat. Okay, and since this is an endothermic, right? That's it. There's our answer, 17.1 kilojoules per mole, and we know it's positive because the two negatives canceled each other out there, and that tells us it's endothermic. And then if you think about it, it is endothermic because my surroundings got colder, which means my system had to absorb the heat. Last question, are you ready? What mass of lithium chloride must have dissolved if the temperature of 200 grams of water increased by 6 degrees Celsius? Okay, so what do we know? We know the mass of water is 200.0 grams, okay? We know that the water changed temperature and it increased by 6.0 degrees, so we know that that's a positive 6.0. We also know that the delta H of solution for lithium chloride is 37 kilojoules per mole. And we know we're playing with lithium chloride, so we might as well get the molar mass of lithium chloride, which is 42.4 grams per mole. All right, I think we've got everything here. So what are we looking for? We are looking for the mass of lithium chloride. Okay, so once again, our equation that we're going to be playing with is moles times molar enthalpy equals negative Q. And once again, I put that negative Q in there because you know that they've got opposite signs. So this is for the water. So this is my surroundings. This is for my system. Okay, so we can solve for n because that's what we're eventually going to need to do. And don't forget that Q equals mc delta T. So negative mc delta T all over delta H. So doing that, let's plug it in. N equals, don't forget my Q is my surroundings, so my mass, 200 grams. Specific heat capacity, and we're talking about water, so 4.18 joules per gram degree Celsius, times the delta T, which was given to us, 6 degrees Celsius, all over 37 kilojoules per mole. So you know the delta H is positive, so you know it's endothermic. This should all make sense, okay? So if we take a look at this situation, okay, let's see here, N equals 0.14 mole. Alrighty. And if the temperature of the water increased by 6 degrees Celsius, because I'm wondering why that's a negative. If it increased, that means this is an exothermic reaction. So that means this has to be negative. That's okay. Now I feel better about this. All right, and lastly, I know after doing my math, so grams cancel, degrees cancel. I made a mistake, and I'm glad I made that mistake because now you can see. Take a look here. This is kilojoules. This is joules. We've got to change, so I'm going to do that right now. Okay, so now these guys cancel. Whew. See how it's always important to make sure things cancel? I already had the answer, and that was the bad thing because I'm kind of going off of a script here. So once we see this, and we're going to 2 significant digits right here, here's my answer, 0.14 moles of lithium chloride, but that's not what the question asked. The question asked for the mass. So mass equals moles times molar mass. So when we plug that in, my moles, 0.14 moles of lithium chloride times the molar mass, which was given to us. Whammo, whammo. And when we finally do all the math, you're going to 2 significant digits to 5.9 grams of lithium chloride. And that is how we do these types of calorimetry questions. So take a look at this. As always, make sure you read section 5.1 and 5.2. These are good homework questions. Take care.